if I have a rotating disk, I can ask myself the question now, which we have never done before, what kind of kinetic energy, how much kinetic energy is there in a rotating disk? We only dealt with linear motions, with 1/2 mv squared, which we never considered rotating objects and the energy that they contain. So let's work on that a little. I have here a disk, and the center of the disk is C, and this disk is rotating with angular velocity omega that could change in time. And the disk has a mass m, and the disk has a radius r. And I want to know at this moment how much kinetic energy of rotation is stored in that disk. I take a little mass element here, m of I, and this radius equals r of I, and the kinetic energy of that element I alone equals 1/2 m of I times v of I squared, and v of I is this velocity, this angle is 90 degrees, this is v of I. Now v equals omega r, that always holds for these rotating objects, and so I prefer to write this as 1/2 m of I omega squared r of I squared. The nice thing about writing it this way is that omega, the angular velocity, is the same for all points of the disk, whereas the velocity is not. Because the velocity of a point very close to the center is very low. The velocity here is very high. And so by going to omega, we don't have that problem anymore. So what is now the kinetic energy of rotation of the disk, the entire disk? So we have to make a summation. And so that is omega squared over 2 times the sum of m of I r I squared over all these elements mi, which each have their individual radii r of I. And this now is what we call the moment of inertia I. Don't confuse that with impulse, has nothing to do with impulse. And this is moment of inertia. So the moment of inertia is the sum of m I r I squared. So this can also be written as 1/2 I put a C there, you will see shortly why, because the moment of inertia depends on which axis of rotation I choose, times omega squared. And when you see that equation, you say, hey, that looks quite similar to 1/2 mv squared. And so I add to this list now, if you go from linear motions to rotational motions, you should change the mass in your linear motion to the moment of inertia in your rotational motion, and then you get back to your 1/2 mv squared. You can see that. So we now have a way of calculating the kinetic energy of rotation, provided that we know how to calculate the moment of inertia. Well, the moment of inertia is a boring job. It's no physics, it's pure math, and I'm not going to do that for you. It's some integral, and if the object is nicely symmetric, in general, you can do that. In this case, for the disk, which is rotating about an axis through the center, and the axis that's important is perpendicular to the disk, that's essential. In that case, the moment of inertia equals 1/2 m times r squared. And I don't even want you to remember this. There are tables in books and you look these things up. I don't remember that. I may remember it for one day, but then obviously you forget that very quickly again. Needless to say that the moment of inertia depends on what kind of object you have. Whether you have a disk or whether you have a sphere or whether you have a rod makes all the difference. And what also makes a difference about which axis you rotate the object. If we had a sphere, a solid sphere, then, so here you have a solid sphere, and I rotate it about an axis through its center. Then the moment of inertia, I happen to remember, equals 2/5 m r squared, if r is the radius and m is the mass of the sphere. My research is in astrophysics. I deal with stars, and stars have rotational kinetic energy. We'll get back to that in a minute. Not in a minute, but today. And this is the one moment of inertia that I do remember. if you have a rod and you let this rod rotate about an axis to the center, and this axis is perpendicular to the rod, the latter is important, perpendicular to the rod, and it has length L, and it has mass m, then the moment of inertia, which I looked up this morning, I would never remember that, equals 1/12 mL squared. And all these moments of inertia you can find in tables in your book on page 309. So the moment of inertia for rotation about this axis of a solid disk is 1/2 mr squared. But it's completely different, the moment of inertia, if you rotated it about this axis. So you take the plane of the disk, instead of rotating it this way, you rotate it now this way. You get a totally different moment of inertia. And most of those you can find in tables.